yesterday, that for an absolute value of some k, the following are equivalent. One, this is non-Archimedean. Two, that the absolute value of the integers is bounded by n. And here are two new conditions that I'm going to add. The absolute value of the integers is bounded by some number, and let me assume that this is non-trivial. And add the fourth condition, that for some n natural, the absolute value is less than 1. So this we already saw. This is clear. 2 implies 3 is easy by looking at the absolute value of A, the absolute value of A n power 1 over n, if A is in n.
You mean 3 implies 4?
That,
what are you showing now?
Sorry, that 3 implies 2.
2, okay.
Okay? Yes, thank you. So the absolute value of A to the n is bounded by m, as it's some element in natural numbers, and this goes to 1. So if it is bounded, it's actually bounded by 1. So we have both of these. And 2 implies 4 is trivial if we know that the absolute value is non-trivial. And for the other direction, let me show that for
Wait.
sorry, okay. I see what you're saying here. That if n is 1, if n, then the absolute value is. Let me talk on Q over now. Okay, maybe just to make stuff simple. Okay, so now it's fine. Okay, so like this. And this is true. Because basically, if n of the n is bounded by 1, take general m in n, write it in basis. And now, so the absolute value of n is bounded by the sum of ai. Each of those ai's is in this setting.
So which implication are you proving now?
With 4 implies 3.
4 implies
4 implies 3. Sorry. Thanks. Each of those a's is in the set, so I can take the maximum of these possible values, because this is bounded by some big M. This is bounded by M times number of elements times the maximal one. But actually, let me do something else. Instead of this, I get this thing. And I can make it smaller if I take the sum to infinity. Because this is smaller than 1, this is bounded by this. Which is some m prime. So the absolute value on the integers is bounded by some number. Okay? So now we're ready to prove Ostrowski's theorem. So let me restate it, maybe. If this is an absolute value in Q, then either this is some power of the usual absolute value from R. Say, not discrete, not bigger. And the second option is that this is some p-adic thing, so some p prime. Okay, so let's prove this. So we argue by cases. Case 1, this is non-Archimedean. Let me define I to be subset of Z having all elements with absolute value less than 1. Then we know it's not empty by the lemma, and it can't be everything. And actually by the lemma we can see that I is an ideal of Z, and it's actually a prime ideal. Prime does not follow from the lemma, just true. So because it's not everything, then and actually it can't be only 0 because of the lemma. I have some pz when p is prime. So if we now take general number x in U, we can write it as p to some power times a over b, when a and b are coprime p, p to power m over b, this is p to power m, and I want to pass to the basis appearing here, so we get this. No, p, p, which is exactly p, which is the standard absolute value, the p absolute value to this power. This is our alpha. Okay.
So why was I prime?
Why I is a prime ideal?
Yes.
Because if I have a b inside, then this is less than 1. We cannot be that both are greater than 1.
Okay.
These are the real numbers. Second case. So, case 2. This is Archimedean. And the reasoning goes as follows. Take some two integers, a, b, and n, and suppose that they're both greater than 1. Then we can write b at the basis of a. So that f minus 1, m is exactly log b over log a, 1. But instead of just writing b, let us write some b to power k, when k will vary here. And the cj's will depend on k, etc. The absolute value of b to power k is bounded by the sum for I. Each cj, well, it's the sum of cj copies of 1, which is bounded in turn because cj is less than a. So this is bounded by a times the sum. So it's a times number of elements times the maximal element, which is either 1 or a to power m. So now let me take the case root of everything. So b is bounded by k. This is just by plugging this log b over log a. So this goes to 1. This goes to 1 because n is of this form. So we get that the absolute value of b is bounded between by the maximum between 1 and this. Okay? Now, we had this lemma that I want to recall, which says that because we are in the Archimedean case, we use 2, there is some n for which the absolute value is at least 1. Let me pick this b and conclude that if the absolute value is bigger than 1, to conclude that the absolute value of a is bigger than 1 for every a in n is at least 1. So we conclude that b is bounded by this, or I have this. But this is symmetric in A and B, so it must be an equality. So this means if I take A equals to 2, I have this, and then basically reading back as I did there, I get that the absolute value of n is exactly n to power log 2 over log 2. So if we take now a general number, rational number, and I have this, which is anything to this power, b to this power, a over b power. So my absolute value is of this form. This is some technical step that it's basically what's happened there, but I don't want to do, if you don't mind. Okay, any questions so far? Okay, now we turn our backs and go to something which is more impressive in some sense, which is the biggest one. What's being theorem? So, what is that? If K is a field with a complete field, with absolute value, which is Archimedean, then either K is the real or K is the complex numbers. And the absolute value on K is basically the standard absolute value to some power. Okay? So maybe the tactics prove this. So by maybe part 2 of the lemma, or part 3 of the lemma if you wish, this field must be of characteristic 0. So Q embeds it. The restriction of this absolute value on Q is Archimedean. It must be of the form is there. So I can complete it and get R. With the same absolute value, standard absolute value. So now there are two cases. Either that there is some I exists in K, and that C embeds in K, or that no solution to this equation. to x squared. Yes. And then we wish to add I and go up there. But this is a bit tricky, so let's start what happens in case 1. So the first proposition that I want to make are Archimedean absolute values on C are of this form. Why? So we have our C and we have this inside. So if omega in C is the root of unity, then this is 1, so the absolute value of omega is 1. But the set of such is dense in the circle for the regular topology, the Euclidean one. Okay? So you do need to show, and this is an exercise, that this map, this is the Euclidean topology, is continuous. This is basically the triangle inequality. Exercise. Or of some sense. This is a bit harder than that. So now you know that on this circle, the absolute value is 1. So now use polar decomposition. And that's it. Theta. Theta. R. And that's all. Okay.
I still don't have any clue why
Why is it continuous? Let me see. It's enough to, because you have homogeneity, it's enough to consider continuity on the circle, right? You know, here's maybe a better way to see this. Okay? This on R, this is the same, something like this, right? So we can look at this at this norm and this norm on R squared. Well, it's not really a norm because it doesn't scale the way it should, but other than that, everything goes. So you can repeat the proof that all norms on R squared are equivalent to each other for these two, because they have the same homogeneity. So they are equivalent. So the topology of this is the same as the topology of this, and this is the same topology as this. I should repeat it. Okay. You know that on R, how it behaves. Basically, well, if you consider C as instead of R squared, then you only use scalars from R. Now, this absolute value scales the same with respect to scalars from R as some power of the standard absolute. Okay, it's fine? Good. This is one way to see this. Okay. So in our case, C embeds into K, and the restriction of the absolute value on C is something of this form. So claim C is K. Why? Well, this is a bit tricky, I admit. So take some alpha which is in K. Sorry. Choose any two, not in C. Well, look at the function tends to infinity, because this tends to infinity, this must tend to infinity. And again, this is a bit harder this time, but this is continuous. Okay? So what you get is that there exists A and C so that M minus alpha is minimal. Let beta be A minus alpha, which is of course non-zero because A is inside C and alpha is not. So what we're going to show is that a very weird claim. If C somehow is smaller than beta, then this happens. This is very weird, I agree. Okay. So why this is true? Pick such C. So for all n, you have that this is true. So I can take absolute value. And by minimality of beta, or A if you wish, this is at least, or each of those is at least the absolute value of beta. So I have this. Therefore, if I now look at this, because, A was chosen to be the minimal element of C, so that, an element of C, so that this is minimal. So if I take this beta and exchange it by something from C, I get something which is bigger by absolute value. Okay, so each of those is at least beta, and I have n minus 1 elements and factors in the product. Okay? So now I have this, which is exactly this, which is by finite inequality, yes, and by choice of C, this goes 1 and then infinity. So B minus C is bounded to beta minus C is bounded by beta, and by minimality of beta I have equality. Okay. But this is absurd. I think this is supposed to be clear. And why is this absurd? Well, I can repeat this claim, replacing beta with beta minus C, and get that this is true for every m integer. But there are many ways to see this, but for example, because I can get to any point in C by taking very, very, very small steps, this implies that this function to begin with is something which is true. So, contradiction. So, now I'll find KC. And the absolute value is what we expect. Okay. Sure.
One other way to see the same claim,
Yes,
is using basically K as a C-star algebra and using the theorem of Gelfand and theorem of C-star algebra.
Exactly. Then, well,
Which is a field.
yes, but then you need to get into, well, for this case it's fine, okay. But you have the case of which is a bit more misleading. I wanted to comment about it in the end. Sure, that's a great remark.
So do you get star algebra structure okay?
Actually, yes, there is a slight sheet here, but
So maybe I should return a comment. The main reason that I didn't use this here is because I don't know that the base, the absolute value on C itself is the standard one. And I cannot somehow rescale it back to be that way. But if I did know that, then it would be fine. Okay? So the second case, this is that the I is not inside K. So what I would want to do is just to drop K and drop I inside and extend the absolute value. For example, as I would like to do so. This is one option. So let me make a remark here. In general, it is true that absolute value goes up to algebraic extensions, but the proof of this is actually based partially on this fact of Swarovski. So I don't want to use it here. For p-adics, it's really not for p-adics. For if you have non-Archimedean ones, it's easier. Maybe give it as an exercise. This is nothing deep. Now, this is a very, very, very delicate point. It's easy to see that, or one can see that x is 0 if and only if x is an element of 0. This is basically this statement over here. And this fact is proven in the same way you would for complex numbers, for example. But a triangle inequality is very hard to impossible to prove. Because if you would try to do the same as you usually do, you would end up with an inequality of this form. When a plus ib and a prime plus ib prime are elements, this is an inequality that you would need to prove. Okay. And you cannot use Cauchy-Schwarz here, because this is a general absolute value. So to treat this in a very, very light way, something needs to be changed. I will go the road of Artin, and in some sense redefine what an absolute value is. Definition, at least this is sometimes called evaluation, maybe it's a bad name. Let me call it quasi-absolute value on K is a map. K to infinity, so that, as usual, x is 0 if and only if x is 0, and it's multiplicative, but I change the triangle inequality to the following weaker claim that there is some universal constant C, so that if B has its absolute value less than 1, then the absolute value of 1 plus B is bounded by C. Okay? And exercise, this is not too hard, but I will give hints that a quasi-absolute value is equivalent, meaning I raise to some power, to an absolute value, and actually a quasi-absolute value is an absolute value if and only if C equals to 2 can be chosen.
What do you mean by equivalent?
If this is a quasi-absolute value, then you can find some absolute value, so that this is true for some power lambda, as we had there before that. Okay? give the hints here, but in the exercise, in interest of time. So the idea now is to prove that this new absolute value on k with I satisfies this property. So it's equivalent to some absolute value on ki. And then we can complete and use what you already did. So in order to prove this, we need
No, it's clear that if you put constant 2,
that it is, okay, so maybe I should remark
Is
on
it?
this. If you put, okay, so the idea is this. Let me notice that if I make this, then I can put 1a1 out. Say that absolute value of a1 is absolute value 2. So this is bounded by this constant 2 times a1. And in general, if I don't make this assumption, this is twice times the maximum. Okay? Now argue by induction to show that now if you sum 2 to the n, such, then this is at most 2 to the n times the maximum of the evaluations. So take now some n, and let me pick the first n ones to be 1, and the last ones to be 0, 1, and it's chosen appropriately to not waste any space. So the absolute value of n, you get that it's bounded by twice times n, 2 times n. And now you repeat the thing that we saw last time with the binomial expansion of x plus y, this trick, but now with more caution, to get that actually what you want holds. Okay, should I make more, this more please? Okay. Okay, so I have 5 more minutes. So just to conclude this part, let me say the following fact, which I only briefly explained, that if K is a field with absolute value, and which is Archimedean, then the absolute value of the sum is at least some constant and the maximum of values. So why is this true? Well, first let me restrict as basically done before, for the case that one of them is 1. So suppose that for every delta I find, now let me be even more explicit. Delta, because of some weird reason that I'll explain maybe if I have time, we choose this like this. Suppose that you chose some A1, which satisfies this. And you look now at A2, which is A1 plus some correction. If you square it and add 1 and choose your correction correctly, then you get something for H1. And basically by this choice of delta, you can continue A3 is A2 plus H2, and A4 is A3 plus H3, etc. And if you choose this delta as you did, this will be a Cauchy sequence which converges somewhere, and this will become smaller and smaller. I'll make this more explicit at homework. So basically you get some limiting guy, A star, whose square satisfies this. Which cannot be if you assume that no solutions to x squared plus 1 is 0. Okay, forgot this is one way to see this. And now, if you go back to this definition of the absolute value on Ki, it's probably the last thing that I'll do today. Then you can just see that this is indeed a valuation. And then you're done. Just let me. Sorry, I'm going to make this take this late. That if I put in all that I want, this is basically saying that if this happens, this is at least this constant delta times the maximum. A squared and B squared. So the absolute value of A of B is at least this. So if you now look at this, and this is A squared. This is just A plus 1 squared plus B squared, which if you use triangular inequality, you have 1 plus 2. Absolute value of 2. A squared plus B squared, then you can bound everything to be constant. 2 half plus, if I'm not mistaken. Yes, right. And this is some constant, which we don't know, but it is. It exists. So this is a valuation. Now you can rescale your equivalency to get actually an absolute value here. And then you use what you already know. So this is a proof of Bigos-Stropski's theorem. And but now we know all Archimedean complete fields that there are. And
So you have to show that this constant is smaller than 2, right?
okay, so you can show this, but actually I'm not sure if you can show this, but what you can do instead is do this. If this is a valuation with constant C, let me rescale it. Look at
It's not a quasi.
yes. Sorry. This is citation in the book that I took these notes from for the first time. So if you now look at this, then this is a quasi-absolute value with constant sigma power lambda.
So there is something wrong with this exercise.
Which exercise?
That something is equivalent to absolute value if a particular C can be chosen. Because now you say that this scaling process, of course, it changes C.
Right, of course.
It is clear. So what does the exercise ask us to do?
Well, if C is smaller than 2, then of course you can make it larger. So if you have, what do you add? What do you want? If the value of B is less than 1, then the absolute value of 1 plus B is bounded by C. So if you put here 1.5 or I don't know what, you can also put 2. So it indeed changes C, but you still have some freedom of choice. Maybe I didn't understand.
What should we show? Because C equals to 2 can be chosen.
It's not
That
an
means-
equivalence, it's that it is an absolute value.
Yes.
If C equal to works for this
Actually,
Yes.
it is.
Yes.
Okay.
This is the first exercise, and from this you can apply this. This is the
Okay.
order of things.
Okay.
Okay, so sorry if I confused you. Okay, so I want to end it today, if you don't mind. And that is all. Thanks for coming. And